What would our lives be like without electromagnetism? Well, guess what? We wouldn't be alive, because without electromagnetism, matter would cease to exist. So then what really is this fundamental concept that holds the universe together? It's the branch of physics which involves the study of electromagnetic force, a type of physical interaction that occurs between electrically charged particles. To get a deeper understanding of this meaning, let's break the word electromagnetism into two parts. First, we have electro, which is synonymous to electricity. And next, we have magnetism, which is synonymous to, well, magnetism. Electricity is defined as the phenomena associated with the presence and flow of electric charge. Looking at an atom, we can see that there is a nucleus consisting of protons, which have a positive electric charge, and neutrons, which are neutral and have no electric charge. Orbiting the nucleus, there are electrons, which have a negative electric charge. These electrons are attracted to the positively charged nucleus, but are repulsed by other electrons. This gives us the common saying in science that lights repel and opposites attract. Another part of electricity that is critical to our understanding of electromagnetism is electric fields. Electric fields are measurable effects created by any charged object that can exert a force on another charged object. Basically, it's a charged particle's sphere of influence. So if any other charged particle enters this sphere of influence, there will be a force applied to them. Also, the particle's sphere of influence isn't as influential as the distance away from the particle increases. Now let's talk about magnetism. Magnets, as you most likely already know, have a north and south pole. Like poles repel and opposites attract. Sound familiar? Magnets also generate magnetic fields, which originate in the north pole and enter through the south pole. But what causes magnetism? What if I told you electricity is the source for all magnetism in the universe? You may be asking right now, but what about bark magnets? They don't have electricity running through them. What if I told you they do? They're made of conductive elements, meaning that they're electrons, which are electric charges constantly moving through them. But then you might ask, why aren't all elements magnetic? To understand this, we have to look at electrons. All electrons are tiny magnets, with a magnetic field coming out of them. If all these electrons align themselves so that their poles are aligned and move throughout the element, then the whole element becomes magnetic. However, this is really rare and only occurs in a few elements such as iron, because most of the time, electrons are not aligned because the shells spin and many other factors. And that's how these two concepts of electricity and magnetism interact with each other that shows the full power of electromagnetism. As previously stated, electricity, or a flow of electric charge, creates a magnetic field. If we change the direction of the flow, then the direction of the magnetic field changes, allowing for the conclusion that a changing electric field produces magnetic field. Alternatively, and more usefully, we are able to convert a changing magnetic field into an electric field and therefore electrical energy through the process known as electromagnetic induction. Basically, this shows that a conductive loop through a varying magnetic field results in the creation of electric current. The most important takeaway is that a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. By far one of the most crucial uses of electromagnetism is to show how light, a form of electromagnetic radiation, works. An electromagnetic wave is created when a charged particle oscillates or vibrates. When this happens, the electric field of the charged particle is changed, which we mentioned before leads to a changing magnetic field, which in turn leads to a changing electric field. And this trend continues on. And so therefore, we create a wave with an electric field parallel to the movement of the particle and a magnetic field perpendicular to the movement of the particle. And this is the way light behaves.